All right, imagine you're a neurosurgeon. Your patient is on the table, and right beneath the opaque bone of their skull lies the absolute most complex, delicate organ we know of. Your job? Hitting a millimeter-sized target deep inside that brain, completely blind to what's underneath without touching any of the crucial wiring around it. Welcome to today's Explainer. We're going to decode the skull's topographical map, figuring out exactly how medical professionals navigate the invisible.
It begs the ultimate clinical question, right? How on earth does a neurosurgeon know exactly where to make that very first incision? How do they essentially develop X-ray vision from the outside? Before we had fancy real-time 3D imaging in every single operating room, surgical pioneers had to rely entirely on external landmarks to guess the internal geography. And incredibly, the geometric maps they came up with, they are still the bedrock of surgical navigation today.
Because here is the bottom line. In neurosurgery, millimeters matter, period. Precision isn't just some nice-to-have academic goal. It's literally the difference between a patient waking up completely fine or waking up unable to speak or move their arm. The stakes are just astronomically high. That's exactly why establishing these exact mathematical maps before even picking up a scalpel is absolutely vital. We're going to look at the beautifully clean, evidence-based rules that make this kind of precision a reality.
Here's our roadmap for today. We'll start with mapping the cranial surface, move into the Taylor-Houghton lines, then locating the motor cortex and finding the Sylvian fissure. Finally, we'll navigate the deep ventricles and wrap up with clinical takeaways and variability.
All right, Section 1, Mapping the Cranial Surface. What's really fascinating here is how the skull acts a lot like a geographical globe. Think about it. Just like a globe has the equator or the prime meridian, the skull has its own specific named coordinate points. We're talking points like the glabella, which is that forward projecting spot right on your forehead, or the inion all the way at the back of the head. These craniometric points, along with the wavy suture lines connecting the cranial bones, act as our solid anchor points to guide surgical explorers.
And out of all those landmarks, one of the absolute most famous is the pterion. It's this incredibly delicate junction where four different bones literally crash together: the frontal, parietal, temporal, and the greater wing of the sphenoid. But what I absolutely love about this is the practical, almost old-school application. Even with all our modern tech, the standard textbook way to estimate its location is just using our hands. It's roughly 2 finger breadths above your zygomatic arch, your cheekbone, and about 1 thumb's breadth behind the frontal process. You absolutely have to know its exact location because there is a major artery running right behind it.
Now, as we know, human anatomy is rarely perfectly symmetrical, which introduces this really dramatic tension between a firm anatomical rule and the clinical reality. Let's look at the sagittal suture rule. That sagittal suture runs straight down the dead center of the top of your skull, and right beneath it sits the superior sagittal sinus, a massive, absolutely vital vein draining blood from the brain. You'd probably think it sits perfectly centered under that suture, right? Well, actually scratch that. It usually lies slightly to the right of the midline in most cases. But, and here's the crucial evidence-based safety limit for surgeons, it's almost never off-center by more than 11 millimeters. That strict 11 millimeter boundary is your safety margin when making an opening.
Moving on to Section 2, the Taylor-Houghton lines.
Now this brilliantly illustrates what we mean by that X-ray vision. By drawing these intersecting mathematical lines right across the curve of the cranium, we're basically projecting a geometric grid onto the head. These solid and dashed lines let us approximate the hidden location of major brain fissures, like the central sulcus and the Sylvian fissure, without ever actually laying eyes on the brain tissue itself.
Let's actually walk through how to build this grid. Mentally draw these coordinates with me, okay? First, we lay down a baseline called the Frankfurt plane. Just a straight line from the bottom of the eye socket to the upper margin of the ear canal. Next, we measure the arc right over the top of the head, from the bridge of the nose back to the inion, and we divide that total arc into exact quarters. Finally, we drop perpendicular lines straight up from the mastoid process behind the ear and the jaw joint. Just like that, using nothing but a tape measure and some high school geometry, we've created a custom, personalized targeting system for anyone's brain. How cool is that?
Next up, Section 3, Locating the motor cortex. So the motor cortex sits right along a fold called the central sulcus, and this fold is the absolute borderline separating motor function in the front from sensory function in the back. Because the motor strip is so critical, early anatomists couldn't just settle for one way to find it. They came up with 4 distinct geometrical methods to pinpoint its location from the outside. Look at Method 2, for example. It uses that arc over the head we just talked about. You connect a point exactly 2 centimeters behind the arc's midpoint to another point exactly 5 centimeters straight up from the ear canal. Having these multiple redundant methods means surgeons can cross-reference their geometry and be absolutely sure they are right where they need to be.
Section 4. Finding the Sylvian Fissure.
Take a look at the highlighted spot here. That's Chotter's point. Now, the anterior portion of the Sylvian fissure actually traces the squamosal suture line on the skull for a little bit, but then it sweeps upward, and it terminates beautifully right at Chotter's point. This exact spot is situated exactly 6 centimeters above the ear canal and 1.5 centimeters above the squamosal suture.
So you might be wondering, why do we care so much about this one tiny millimeter exact coordinate? Well, because exactly a 4 centimeter craniotomy, a 4 centimeter circular window cut right into the bone, centered perfectly on Chotter's point, gives you absolute ideal access. It perfectly exposes the exact blood vessels in the angular gyrus that neurosurgeons need for really intricate bypass surgeries. The geometry literally dictates the success of the surgery.
Which brings us to Section 5. Navigating the deep ventricles.
Okay, here we're looking at the ventricular system buried beneath the skull. And honestly, it is remarkable. Even structures located 4 to 5 centimeters deep below the outer surface of the skull, like these lateral ventricles, they align completely predictably with lines drawn on the external surface. For instance, the dead center of the lateral ventricle aligns with a line drawn straight back from the mid-pupillary line of the eye. It is an incredible piece of 3D spatial relationship.
And the research backs this up with highly specific clinical data. Just look at dimension D2 here, the distance from the bony clivus to the floor of the fourth ventricle. It averages exactly 36.1 millimeters. Having these reliable average baselines, along with the established upper and lower limits, gives a surgeon a very safe mathematical envelope to operate inside, which is absolutely crucial when you're working deep inside the brain where visibility is practically zero.
Finally, Section 6. Clinical takeaways and variability.
So here's the true clinical reality check. On one hand, you have this beautiful, elegant precision of the topographical map, mathematical lines giving us reliable approximations of hidden structures. But on the flip side, we have the sobering reality of human biological variation. Remember that incredibly critical motor strip we mapped out earlier? Yeah, well, in reality, it can lie anywhere from 4 to 5.4 centimeters behind the coronal suture. That is over a centimeter of variation for literally the most important functional real estate in the human body. And to make it even wilder, even when the skull is wide open, the central sulcus can't always be reliably identified just by looking at it. The map gets you to the right neighborhood, sure, but it definitely does not guarantee the exact address.
Which leaves us with a pretty provocative thought to wrap up today's explainer. If these external maps and exact geometries are ultimately just approximations, what modern technologies must we combine with them to truly eliminate that surgical uncertainty? The answer is merging these classical, brilliant topographical principles with cutting-edge functional MRI and real-time computer neuronavigation. It's this perfect, necessary marriage of historical anatomical genius and modern technological power. Thanks for joining me to decode the invisible map of the human skull. Keep asking questions and keep exploring the evidence.